Today the talk is called HPC Made Easy, working with HPC systems through graphical interfaces. My name is Nick Dushek. I'm one of the sysadmins at CCAST here, which is NDSU's Center for Computationally Assisted Science and Technology. So we provide advanced computing resources, support, and consulting to the NDSU community and affiliated researchers. That's kind of what CCAST does in a nutshell. And today I just have a few slides. Most of it's going to be interactive, but we'll just briefly kind of go over the evolution of advanced computing, talk about the growth in the different number of research disciplines that are using advanced computing and what that means for how we provide resources to HPC users. We'll just talk a little bit about what HPC is and HPC architecture, because when we use the web interface, it helps to kind of have an image in mind of how these things are organized in the physical world. And then we'll just talk about the traditional way that people interact with HP resources, and then how they interact with HPC resources using a graphical interface such as Open on Demand. And so, you know, if we start here in the 70s, this is kind of when the first, I guess, quote, supercomputers came on the scene, and their use was really limited to physicists doing really kind of specialized research of computing. Then we get kind of into the 80s and 90s, and these systems become a little bit more commonplace. The physicists kind of bring engineers on board. And so the user community broadens a little bit in what types of disciplines are able to use advanced computing. In the 2000s, we start to get a broader kind of group of scientists and engineers. So again, HPC resources are becoming more accessible, but still pretty specialized. And then into the 2010s, so finally we're starting to see really broad adoption of advanced computing. High performance computing. And so this is everybody from, you know, scientists and physicists and engineers like we had previously, but also people in business, medicine, artists, economists, social scientists. And so that means a few different things for what centers like CCAST have to do to accommodate all of those users. And so, you know, just when we say advanced computing, we kind of think of three main areas of advanced computing. There may be others, but in the middle here we have high performance computing, and we'll talk about specifically what that means. But when people hear the word supercomputing, that's analogous to high performance computing. There's this other kind of branch of computing called high throughput computing. And we won't talk a lot about that today, but that's people who are running many thousands and thousands of small processes on lots of different computers at the same time. And then what may be familiar to some of you in recent years is big data, visualization, things like data analytics, et cetera, that need really high performing computers, but they're not used in the way that supercomputers are traditionally used. And that will kind of touch on what we talk about today. So I'm just going to show some stats from CCAST, but I imagine that Aaron from UND will attest that this is probably very similar for them. You know, this is just our number of different research groups using CCAST from 2012 to 2020. So you see, you know, in 2018 there was a big uptick, and then it's been growing, you know, a little bit more slowly, but still growing. And when we look at where these different research groups come from. So this was in 2016 and is 26. So 26 research groups, 12 of them we didn't have classified, but you can kind of see some of the typical groups that I talked about in the early stages of research computing. So physics, chem and biochem, engineering, mathematics. We're starting to see some of those kind of life science fields, economics, but by and large, it's mostly physicists, engineers, materials scientists, chemists in 2016. And if we jump forward to 2020, we see that the number of research groups has almost tripled from 2016, and a much greater diversity of fields. And you can, some of them are labeled on the side here, but you can see we have people from plant science, animal science, accounting, economics, stats, pharmacy, communications, as well as other institutions. And all these people have different needs, and they come from different comfort levels with using advanced computing. And so if we start to talk about what is high performance computing, it requires significantly more computational resources than the average workstation. So people come to high performance computing because they can't do what they want on their workstation. It typically uses like a low latency, high bandwidth network. So we have a lot of computers coupled really tightly with fast networking, so that they can communicate with each other at high speed. And we'll show kind of what that means in some following slides. Typically, it's equipped with a high throughput storage system. So usually that's a centralized storage system so that all of the different kind of computers in the cluster can see the same files, because they're going to be talking back and forth. So they need to see the same information. And then it usually requires concurrent or parallel computation. So many computers working on the same problem at once. And that's where that communication that I mentioned comes from. And so we need HPC when we want to solve problems faster. We want to solve more complex problems, really big problems. Maybe we want to analyze a lot more data than we can fit on our local disk drive. And then if we want to save time and personal resources. So just to give an example of that, if you've ever tried to run an intensive program on your laptop, you might be able to get it done, but it's kind of consuming your laptop, for the whole time that's running, and you can't do anything else with your computer in some of those cases. And so we can send those processes to an HPC cluster and free up our own resources to do other things that we need to do. So I'm just briefly going to talk about HPC architecture. I don't want to get way down in the weeds, but like I said, it helps if you have some kind of mental image of what we talk about when we say the supercomputer or the HPC cluster. So a cluster has many nodes. A node is like an individual computer or an individual server. So here, there's a picture of this Raspberry Pi cluster. Each one of these little computer boards would be a node in this small cluster. And this is just kind of a toy or a demo cluster to illustrate HPC concepts, but each one of these would be a node. In the picture on the right, in the Thunder cluster, we have many individual servers that are each nodes. And each node contains one or more sockets. So you can see in the diagram here, we have the light blue outline for a node, and a socket is just a place where you can put a CPU or a central processing unit. So each socket holds one processor, and each processor can have one or more cores. So when you think of cores, you may have heard that your laptop is a dual core machine or a quad core machine. In HPC, it's very common to have CPUs that have 20 cores or 40 cores, or our new cluster that we're deploying has some cores that have or some CPUs that have 128 cores. So that means, in one node, a socket has 64 cores, and it has two sockets to make 128 cores. And a core is just something that can run a computer process. So in general terms, you can think of something with 100 cores as being able to run 100 processes at 100% at the same time. In reality, computers are running thousands or tens of thousands of processes at once, but they all take turns and they use the same cores. So that's one node, and a cluster can have tens or hundreds or even thousands of tightly coupled nodes. So the picture on the bottom left here is a picture of a server enclosure. So this is one kind of rack mount server chassis, And inside it, there are actually 4 of these nodes that pull out. So each of these trays that slides out has its own CPU with its own cores and its own memory. And then in our Thunder cluster, we may have we have 20 or 40 of these for which adds up to about 80 to 160 nodes. And in the bottom right, you can see kind of a different type of node, but each one of those blue lights basically is an individual server that has its own resources. And the power of HPC comes from the fact that we're able to connect together a lot of these cores and direct them at one single problem. And so in addition to the nodes, we usually run a Linux operating system. We have several networks, high-speed networks for data and management communications. And then we have a high-performance storage system and a batch system or a job scheduler. And we're going to talk a little bit more about the job scheduler in some following slides. And then we just have scientific software, which are the applications that researchers want to use on the cluster. And so this diagram kind of helps you visualize just in an abstract sense what an HPC cluster looks like. So we have at the top, we have a login node, and this is where our users connect to the HPC cluster. And then the login node is connected via a switch to all of the other compute nodes in the cluster. And so these compute nodes are the nodes that are going to do the work, that are going to run the researchers' computations when they submit them. And then down on the bottom here, we have these red lines connected to this FDR InfiniBand switch. This is a little bit older diagram, but this is the really high-speed data network. And the green box in the bottom right there that says GPFS. That's our parallel file system. So what this is just showing is that on the top we have the way that researchers gain access to the cluster. And then on the bottom, we have kind of what happens in the background, how the nodes access the data the researchers put there, and how they're interconnected for fast communication. And so I briefly mentioned the batch system for the scheduler. The scheduler is, you can envision it as somebody who's kind of accepting requests for work, and it's going to portion out those requests to the different compute nodes. So the scheduler sees all of the nodes. It sees what they're doing and how many resources they have available, and that it uses to determine where it can send researchers jobs. So if we have our 4 researchers up here, we can imagine the scheduler as somebody saying, please submit your resource request and I'll find some resources for you. And so Miss A says she needs 4 nodes. So there's the scheduler assigns these 4 nodes in red, and now these nodes are unavailable, to other researchers. So then this researcher needs 5 nodes. The scheduler assigns 5, 2, 6, and so as many users are submitting jobs, all of these nodes become occupied and they can't be used for other things. People can delete their jobs, or if their job's finished, those nodes will be released for more work. And sometimes people need, whole banks of nodes. For example, this person needs 32 nodes. And like I said, this is kind of where the power of HPC comes from, is being able to use many nodes with many cores on each node, all to attack a problem at once. And so it might help next to kind of talk about what does it look like to submit a job. So I've been talking about a job. A job is just a task that a piece of software is going to run. And in order to submit a job, you have to write a job script. So this is a list of instructions that are in a specific format that tell the scheduler what you want to do and how many resources you need. And to write your job script, you have to find an appropriate queue. And you have to see how many resources are available. And so this slide is kind of designed to be messy because it's a lot of text. And that's because this is the way that people traditionally have interacted with HPC clusters. So traditionally, users have used a text-based terminal. And there's a picture down here of kind of what that looks like in my account. And they log in remotely and they enter Linux commands. And you need a command to do everything from editing files to submitting and monitoring jobs. And when you get good at this, this is a really efficient way to work with the system. But a lot of new users find this intimidating, and there can be a steep learning curve. And so that's why we talk about graphical interfaces for HPC. In recent years, they've had several web-based portals that have been developed for HPC resources. Some of them are free, some of them cost money, and they're a little bit more approachable for new users. But in addition, they have frameworks for running interactive applications and other workflows. And this is important because, as we talked about earlier, we have kind of this explosion of users coming from fields of science that aren't typically associated with high performance computing. And so they're not going to have the same needs as physicists and engineers and chemists always. They need different applications. They may want to work with big data or do data visualization, or just have a desktop session that has more resources than their personal desktop. And so that's kind of the impetus for this Open On Demand project. So Open On Demand is a web HPC portal. It's developed by the Ohio Supercomputing Center, and it's free and open source for centers like us to deploy and maintain. And so what you'll find is this has been very widely adopted, and there are a lot of HPC centers all over the US and in different parts of the world who use this same HPC web portal to access their HPC resources. And so at this point, I'll kind of leave off with the slides, and I'm going to switch my screen sharing to a web browser here. So can everybody see that? Okay, I'm going to assume yes. So this is CCAST's Open On Demand portal. And this you can think of from the previous diagram where I showed the login node where users are logging in. So this is actually running on a login node. So in a way, this is connected through this web browser to all of our hundreds of compute nodes that are in our HPC cluster. And the way we interact with those is through different kind of plugins that are available here on the top bar, and we can do different things with these. So if you log into this, and I don't think many of you will have access at this point, but when we log in, we just have some basic messages and some policies here. The first thing I'll show is the files menu. And in HPC, your home directory is kind of your landing point for all the work that you're going to do. So when you log in, you're placed in your home directory, and from here you can navigate to other directories that you have or subdirectories. But this is going to be very familiar to anybody who's used kind of like a Windows-based file explorer, or even like the file explorer in Mac. You can click into various of these folders. You can see your data here. So I have some files here. You can upload and download data. So you can upload from your workstation, or you can download to your workstation. And you can even view and edit files. So for example, if I want to edit this loop.pbs, there's a built-in file editor, and I can make changes here, and then those changes get reflected in the file on CCAST. And so the important thing to remember here is that this is a remote file system. So this is not available to our local computers. This is on the shared file system of the HPC Center. And like I said, there's traditionally people have used a text-based terminal. So in a lot of places in Open On Demand, you can open locations in a terminal. if you kind of are a more advanced user or you feel more comfortable doing things that way, you can open a shell and then it'll log you in that way, and you can actually run commands here in the terminal, but still through your browser. So this is very kind of very intuitive if you've worked with a file explorer before. I won't spend a lot of time on that, but we can go back to it if people are interested. Here in the jobs menu, we'll talk about a couple things, but if you remember, a job is kind of the unit of work. So when a researcher wants to do something, they have to define a job and then they have to submit that job to the cluster. Right now, I don't have any jobs running, but we can switch this to all jobs and we can see, so these are all the jobs that are running on CCAST right now. And we typically refer to this as the queue, just meaning the list of all jobs that are either running or waiting to run. So we can see that, here there are quite a few jobs running. There are 293 jobs total, either running or queued. And it's not going to show us the user, but we can see some information about the job. So we can see, it has a job ID, a name. It shows how many CPUs have been requested. It shows what node it's running on. So this is the actual compute node that it's running on. And then it shows like some stats about memory usage. It shows the script that's being run. And so each of these, 300 or so jobs were created by users and submitted to our HPC cluster. So the other part of this jobs tab here is the job composer. And this is really, really nice because if you remember where I said, how do we submit a job, but we have to write a job script. The job scripts are kind of clunky to write from scratch because you have to have all of these kind of keywords and things in there. But through Open On Demand, we have a set of template jobs that we can start from that kind of give people a better idea of what they need to do to create a job script. So I'll just look at one here. We have a Python example. If we click on the Python example, on the side pane here, it brings up, the name of the job, the cluster that it's going to submit to, and then it shows us the files that are associated with this job. Okay, so from this template, we can create a new job, and then we can kind of modify it to suit our needs. So we can look at what's going on in here. So the job folder contents, so you can see it copied it to a location in my home directory. Here's the name of the script that will be submitted. And we can actually open this in the file editor and kind of explore what it's doing here. And so just to kind of walk through these options, I know the font is probably a little bit small. Let's see if we can, there we go. So all of these lines that start with hashtag PBS or pound PBS is some instruction to the scheduler. So it's some way that we tell the scheduler what we want it to do. So this first line is we're setting the queue -q to default. So there are different queues that we have access to that have different kinds of nodes in them. And the simplest one is just to say to use the default queue. We give our job a name. And that's because when we look at jobs here, they're going to show up with a name. And that's just a way for us to identify which jobs are ours or to remember what we did. And then here's where we're selecting how many resources we want from the compute nodes that our job is going to run on. So this is saying select one node. We need 2 GB of memory and we need 1 CPU core. So this is a very small job. people request 20 or 40 CPU cores per node. They may request multiple nodes. So they may request 2 or 5 or 10 nodes, but we're just requesting one. And then we're saying that our job should not run for more than 8 hours. If it does run for more than 8 hours, the system is going to kill it. And so this is kind of where we have to estimate how long do we think our process needs to complete. And then we just say here which group we belong to, just for kind of tracking purposes of which groups are using the cluster. And then we get kind of into the basis of our script. So here we're loading Python version 3.4.3. We're changing into the PBS working directory. So this is the directory that we're going to submit our job from to make sure that all the files end up in the same directory. And then we're going to run this Python script, sample hello world.py. And so that is the other file. If we see here, now I'm all zoomed in. If we see here, this is the other file we have in our job folder. And all this script is going to do, for those of you who are familiar with Python, it probably looks pretty simple, but it's just going to check to see what version of Python we're running. If it's version 3 dot something, it's going to say, hello, you're using Python 3.x. If not, it's going to tell us we're using 2.x. So since we're loading Python version 3.4.3, we would expect that our job is going to output this. So for now, I'm just going to zoom out a little bit, back to kind of normal. So we're happy with our job. We're ready to submit it. You can see here it says not submitted. So what we're going to do is we're just going to click submit. Now it says it's running. And actually, if we look in my jobs, I can see now that I have a Python job running. The system has assigned it a job ID, has the name that we gave it. This was our resource request, and it shows where the output file is going to be directed to. And so that job ran pretty quick. We can see it's already changed to completed. And now our folder contents have been updated and we see this output file. So if we click on that, like we expected, outputted, hello, you're using Python 3.x. So that's kind of a trivial example. I won't do too many more examples, but I will say we have, a lot of examples for all sorts of different software packages. And if you, are using CCast, and you don't see your software in the list of examples, we could always help you create an example. But we have kind of a pretty good catalog of different software. And, we can look at maybe a little bit more complex job to just see, so this job has 4 data input files that it needs. In addition to the job.pbs file, and we can see here that this this command is a little bit more complex. There's more going on here. Some job scripts can get to be 100 lines long. Some can just be a few lines. What we're hoping eventually, what our plan is even to kind of take this process of creating a job script and put this into a graphical user interface too, so that users don't have to look at something like this. They just have a form that they can fill in that says, here's how many CPUs I want to use, here's how much memory, this is the software I plan on using. And so those features will probably be available in later versions of Open On Demand. But for now, this already kind of makes it a little bit less intimidating than having to work just solely in a text terminal and just type commands. The last thing I want to show is this interactive apps drop down. So I'm going to click Thunder Desktop here. And so this is, these are interactive applications, meaning applications that are going to launch with some sort of graphical user interface. So when we were working in the job composer here, we created a job, we submitted it, and it kind of ran in the background, and then it told us it was done, and we examined the files to make sure they were what we expected. That's called batch computing. So you submit something to run in a batch, it runs, it tells you when it's done. With interactive jobs, and I got to figure out where I put my, okay, here we go. With interactive jobs, we're actually going to be working on a compute node in real time, just like we would work on a desktop computer. The difference is it'll be presented to us in the browser. And so this first one we have is Thunder is the name of our cluster. So it's a Thunder desktop session. And it says it's going to launch an interactive desktop on one or more compute nodes. And you'll have full access to the resources these nodes provide. And so we get to pick an amount of time that we're going to run. Currently, we have a max of 8 hours. And I'm just going to say that I want the equivalent of like a decent high-end workstation. So 4 cores and 16 gigabytes of RAM would be something that, you know, would maybe be a nice laptop. We could go up to, you know, 20 cores, I think. I guess 10 with this app. But we can use more resources than this. I'm just going to use this number of resources. And so we can click launch. And you can see it's starting the job with on our one node with our 4 cores. Gives us a session ID. I'm going to just delete some of these here. So it gives us a session ID, and we can click that, and it shows us the folder location where this job is running. And these are just all different pieces that the job needs to run. So now we can see that it's started, and we have a lot more options now. The first thing is, since we're running a job, we can always open the terminal on this node, and we can interact kind of in the old school text-based terminal way that I was talking about earlier. I'll just leave that to kind of load. Here underneath that, we see when the job was created, how much time it has remaining on the session. We talked about the session ID. And then before I launch the desktop, I'll just comment briefly on this. These sliders, image quality and compression, are adjustable. So if you have a low bandwidth internet connection, you can kind of lower the image quality, you can increase the compression. Both of these will result in a smaller amount of data being transferred over your internet link. Because what we're going to do is we're basically going to be kind of streaming video of, you know, this desktop session. So since I'm on campus, I'm just going to leave them pretty high up, and I'll click to launch the link. And we can see here, this looks like a basic computer desktop. It's a Linux operating system, so it may not look very familiar to Windows or Mac users, but I mean, intuitively, it has applications here. We can click, you know, File Explorer locations. We can see our home directory. We can see other drives, places we have access to. We can launch it built-in applications, so we could launch a terminal here if we wanted. We could launch a browser, although I don't really use a browser in these, so I'll save that for another time. And we can even launch graphical applications within this desktop environment from the terminal. So I'll leave this running for now, and I want to show a couple other interactive applications. But the nice thing about this is that like I'm not sure how it's coming through over Zoom, but this is on my end is actually pretty responsive. So it's almost like I'm working with a local computer, but this is a desktop that's running in my web browser on the remote HPC cluster. So the other interactive app I'll show is, we'll show MATLAB. Some of you may have used MATLAB. It's popular in certain fields of science. But basically what this is going to do is it's going to launch kind of an interactive desktop, but an interactive desktop that only has one app, and that's MATLAB. And so once this launches, we'll have a launch button that we can click and open the MATLAB user interface. And while that's, oh, okay, it's already started. We can open this up. And MATLAB can typically take a little while to load. So we'll kind of let that load. Over here, I'm going to launch another one for RStudio. So if you do biology research, any sort of statistics, you've probably used R or RStudio. This is kind of a web server based application. So it's made natively for the web, and it just looks like you're using a website. That's always the worry with live demos, is that the demo won't load. So MATLAB looks like it's taken a little while, but we can look at RStudio server here when it launches. And so one thing I'll mention is that these interactive applications, we've developed some of these, but users in Open On Demand, if you have, if you're good at web development or software development, you can kind of create your own interactive applications in Open On Demand and share them with your group. And so this is the RStudio interactive application. Takes a little bit to load, but yeah, and so this should be familiar to anybody who's used RStudio before. The important thing to remember is, again, this is not running on my local machine. This is running on a compute node 122, on our HPC cluster. And so the cool thing about this is that it's like we're working on our desktop with RStudio, but it's connected to all of our files on CCast. And so we can run, whatever R code we would normally run here on the HPC cluster interactively. And then later, if we want, we can transition it to a batch job if we want to run, a lot of simulations or something like that. You can see MATLAB is going, but it's just taking its time. MATLAB is pretty resource hungry, so I maybe should have requested more cores, more memory, but it will load, and then it'll show just kind of the basic, MATLAB GUI. But in a nutshell, that's kind of how we do graphical interfaces at CCast. And like I said, a lot of institutions use Open On Demand. What's really nice about these things is that we could, exit out of all of these windows. We can change the screen, and still all of our interactive sessions are just kind of set aside for us. We can go back to this screen. We can reconnect to any of these as long as they're still running. And so it's kind of nice that way that, it's not like your computer where you have to worry, okay, if I close my laptop, is it going to go to sleep and it's going to stop doing the thing that I had it doing? These are all just managed in the background for us, and they're kept here until they expire when they hit their time limit.